very excited to introduce Matt O'Toole. Matt is my academic nephew. So he did his PhD with Kyros Koutolakis at the University of Toronto. And Kyros and I were office mates in grad school, and we published a bunch of papers together. So that means that I have a Matt O'Toole number of 1. Like an Erdős number, and I'm hoping to improve that. So Matt has been at Stanford for the last 2 years, is that right? Doing a postdoc there, and he does really cool work at the intersection of photography and computer science, and he's going to be telling us about that today.
Great. Thanks, Steve. Hi. I'm going to talk about computational imaging. And this is a topic that involves looking at the intersection of optics, algorithms, hardware, all these different elements to create new computational cameras and computational displays. And examples of computational cameras include imaging techniques that are able to capture HDR images. This is a technique that you can find now on your smartphone and allows you to capture images that look a lot more vivid, that is, capture detail in both bright and dark regions within a scene. Other systems that capture super resolution images or light field images. Light field images allow you to refocus images after they've already been captured. And a lot of these concepts are also applied towards displays. So you have HDR displays, super resolution displays, and light field displays. So light field displays, as an example, allows you to experience 3D content without the need for special 3D glasses like those that you wear in a theater. And my interests happen to lie at the intersection of the two. That is, I'm really interested in computational cameras and displays that allow us to analyze light transport. That is, use light from a display to send light signals into an environment and use computational cameras to measure the response. And this can be used for all sorts of different applications. And for today, I'm going to focus on 3D imaging. And the reason I want to talk about 3D imaging is that it is a topic that has been very used in the recent years. So basically, there are a number of new growing industries that are making use of 3D sensors. And examples of that include the autonomous vehicle industry. So these cars are really reliant on having sensors that can capture the 3D environment in an accurate and robust way to allow them to be able to navigate through them safely. So for example, this particular sensor is called a LiDAR. It's a light detection and ranging system. And it works by sending out pulses of light into an environment and measuring the time it takes for light to travel through the environment, hit an object, and come back to a detector. And this is a time-of-flight technique. It measures the physical time it takes for light to propagate in order to infer distance. And it produces point clouds that look like this. Other examples of 3D sensors include those that you can find now on your iPhone X. So the iPhone makes use of something known as structured lighting. That is, it sends out these structured lighting patterns, these dot patterns out into the environment, say on your face, and uses a camera to capture that response from a different point of view. By looking at how these dots were transformed by the geometry of your face, it can infer 3D shape. And it uses it for detecting whether the user of this iPhone is present, and they'll unlock the device only if it can accurately capture that shape of your face. Another example of 3D sensing as its use is its use in VR and AR. So VR, of course, presents virtual content to a user, and in order to capture that content, you may need to use a 3D sensor to capture, say, the environment of a museum, and so that you can actually experience that within your living room. But another example of active sensing, or 3D sensing, is the use of these HTC Vive lighthouses that actually are projector units that you mount into the corners of your room. And the HTC Vive detector basically has these little light-sensitive detectors on them that pick up the illumination that's sent out by these lighthouse units, and they use that in order to track the 3D position of the head-mounted display within the room, so that you can basically walk around the room and experience virtual content throughout your living room. Another use case for 3D sensing is that of augmented reality. So augmented reality, the goal is to really mix virtual and real-world objects together. So if you have say, a virtual object that you want to interact with a real-world object, say a ball that's bouncing off a desk, then you need to know the geometry of your desk so that you can basically simulate those physical interactions in an accurate way. And all these devices basically are composed of 3 different elements. The first element is that of a scene. You have a scene that you're working with, and you have a light source that's used to illuminate that scene. So in this case, let's say you have a projector, and I can control the structured light patterns that go into an environment with this projector. And then you have a sensor of some sort that captures the response from, say, a different point of view. In this case, I have a camera here looking at this bunny from a different point of view. And whenever you do imaging in this context, there are a number of different light paths to consider. So light can interact with the environment in a number of different ways. For example, you have these direct light paths as an example. These are light paths that start from your source, hit an object at a point in space, and come directly back to a sensor. You also have indirect objects, or indirect light paths. These are light paths that scatter multiple times before reaching a sensor. So in this case, some light hits this bunny in its ear, then its body, and then returns to the camera. And you might have other forms of indirect light paths, for example, those that are reflected rather than scattered, say by a mirror within the scene. And your normal camera, your normal sensor, picks up all these different light paths, regardless of how they interact with the scene. And this is a problem for 3D sensing, because when you're wanting to do 3D sensing, you're really only interested in these direct light paths. These are the light paths that give you the information about a scene. And you're usually going after the length of this light path or trying to make use of where they triangulate in space. So sometimes you try to identify which camera pixel and which projector pixel are paired together to see how they intersect in 3D space. But when you have all these other light paths in the mix, you get really poor reconstructions of 3D shape. So for example, in this case, I have this mannequin head on the right, and there's a mirror in the scene. And the mirror causes indirect light transport to be present. And this is very problematic for these 3D scanners, because the indirect light basically starts to interfere with the direct light. And as a result, the portions of the scene that contain indirect light are not reconstructed properly. So you can see that there's all these missing portions to the face here, and this is due to the light scattering off the mirror. Now I'm going to talk about the concept of transport probing. And this is an idea of building cameras that are capable of selectively choosing which light paths you measure from a scene. And specifically, I'm going to focus on, for the first half of the talk, on probing for these direct light paths. That is, light paths that only scatter or reflect off an object once within the scene before coming back to a camera. And we'll use that form of imaging in order to produce much more reliable forms of 3D shape acquisition. But direct light paths aren't always present. So sometimes when you're trying to image an object, there may not be any direct light paths interacting with that object. So for example, here I have a camera system on the right. I have an object on the left, but there's an occluder in between. And the occluder prevents any light from traveling from my system to the object and back to the system. In this case, indirect light is, however, interacting with the object. And for the second half of the talk, I'll focus on how we can use these indirect light paths to illuminate a wall, which will reflect light back to this object, back to the wall before being picked up by the sensor to produce this type of image. So before talking about using these direct and indirect light paths in order to capture the 3D shape of the scene, I'm going to focus a little bit more about what I mean by transport probing. So as I mentioned before, a conventional camera captures images like this. So this was an image captured through flash photography. So I have a flash bulb that illuminates this person's face, and I have a camera that picks up the response. And whenever you perform this type of imaging, light will interact with this face in all sorts of ways. So there's some light that reflects directly off the surface of the skin. There's also light that travels beneath the skin, bouncing around multiple times before it gets picked up by the camera. Now, the idea behind transport probing is to provide a user with the ability to select which light paths a camera actually picks up in order to produce images like this one. So this is an indirect-only image. That is, this is an image that only records the light that bounced around the scene multiple times before reaching a sensor. So for example, The teeth here appear white because teeth are translucent. When light hits teeth, it scatters within them and bounces around multiple times before returning to a camera. And so our camera here is picking up the light from the teeth. That's why they appear bright white. The skin, on the other hand, appears much more red. And that's because what you're picking up is the light that's traveling beneath the skin. And it's picking up the color of skin, which is due to indirect light transport. This might be a little bit dark here, but these portions of the face contain white highlights around concave regions. That is, regions where light is diffusely interreflecting between different points on the face. So you have light traveling, say, off one part of the face, then grazing off the nose, and that's captured through indirect light transport as well. And what's really interesting about this form of imaging is that this is actually a raw photo. So the process to capture this image required no computational processing whatsoever. So all the quote-unquote processing that went into capturing this type of image was done optically through controlling the light that goes into the scene along with the light that comes out of the scene through this form of computational display, computational camera kind of mix. So if we want to capture an image like that, the goal is to basically block these direct light paths from contributing to an image, right? So it's these one bounce red direct light paths that we want to eliminate. So how do we do that? Well, it turns out there's a very simple constraint that we can use to identify which light paths are direct and which light paths are indirect. So the direct light paths have to satisfy something known as the epipolar constraints of the system. What this means is that the light that travels along direct paths have to travel from one epipolar line, which starts at a projector plane, and that light will have to map to some pixel on a corresponding line on the image plane. These epipolar lines are determined by the geometry of your light source and cameras, projector and camera in this case. And it's completely independent of the scene itself. So the scene can have any kind of shape, and it's completely independent of how these direct light paths will have to travel through the scene. That is, it has to start from one epipolar line and end up on a corresponding epipolar line. The indirect light, however, can start and end on any pair of projector and camera pixels. It doesn't have to satisfy this epipolar constraint, right? So light can travel from one point on your projector, go through the scene, and can bounce around multiple times and end up on any camera pixel. And there is some amount of light that travels along corresponding epipolar lines through indirect light paths, but it turns out that these are a very small fraction of the total amount of light within the scene, and you can pretty much just ignore it. So let's say we want to capture an indirect-only image. Well, we can do the following. So we can start by illuminating all projector pixels, turning on all projector pixels except those on a specific epipolar line, and then only exposing the camera pixels on the corresponding epipolar line. And because we made sure not to turn on the epipolar line on the projector along with the epipolar line on the camera at the same time, we ensure that no direct light paths can ever actually make it from the projector through the scene and to the camera. Only indirect light paths will be exposed, or these pixels will only be exposed to the indirect light within the scene. But this is very inefficient or not very useful because all you're doing is exposing one line of camera pixels on your sensor. So we can go a step further. So instead of just one line, we can turn on half the lines on your sensor. So expose half the epipolar lines and illuminate the scene with the complement of that pattern. And again, so long as we illuminate the scene with the complement of the epipolar lines that you use or display on your camera, then you ensure that no direct light paths will ever reach your sensor. But again, it's not very useful because, well, now you have all these black lines. Yes?
I don't understand something. So don't you need to know the location of the object in order to identify which corresponding pixel?
It's a good question. And it turns out that no. The reason it's not, you don't need to know the geometry of the object is because the only thing that changes when you know the geometry of the object is which, let me back up here a couple of slides. So the geometry of the object will determine which pixel along this epipolar line will be exposed. but that's the only thing that changes. So even if the scene is different, the light will have to fall along this epipolar line. There's no scene with no shape that exists that will allow the light to travel directly to another pixel on this camera sensor. Does that make sense?
No. If the angle of the object is slightly higher, wouldn't the light go higher?
So this is a diffuse scattering event. It's not a specular reflection. And we're dealing with projective geometry. And so if you were to think about the possible combinations of how a light path will have to deflect to reach our camera, there's a 1D set of positions at which it can scatter. So the light, if you think of this as the projector sending out a ray into the scene, at some point it's going to scatter, it's going to hit an object in space, at which point it's going to trace a line from that point directly to the camera. The intersection of that ray with the image plane of your camera will tell you which pixel is basically getting exposed. And the 1D set of possible points that light ray will get scattered corresponds to this 1D line at which which pixels can basically get illuminated or exposed. Okay. So through this process of only exposing complementary epipolar lines, basically you make sure that you never illuminate a scene with one epipolar line and expose the corresponding epipolar line in your sensor, regardless of the scene geometry. You're going to always make sure that you block the direct light, because you know from this epipolar geometric constraint that no direct light will ever make it to the sensor. But again, you only have half the pixels exposed, so you can repeat this process multiple times for different illumination and mask patterns, and basically integrate the result of many different illumination mask patterns pairs to create an indirect-only image where it's more evenly exposed. Your sensor is evenly exposed. All the camera pixels receive effectively, on average, the same amount of exposure time. Yes?
Is this not going to eliminate some of the combined not indirect reflections? Because each one, all the pairs, you're missing half the possible pairs each time.
Yeah, that's a very good question. And if you're only dealing with, say, two patterns, where you're illuminating the scene with one half and then illuminate the scene with the other half, there are all sorts of light path, indirect light path that you might be ignoring. Or you might get an uneven contribution of certain light paths versus others. And the solution to that is actually to integrate across many, many different illumination mask patterns and randomize them as much as possible. And by basically repeating this over, say, n patterns where n is relatively large, and dealing with n kind of random different patterns, you kind of uniformly, you average all that out. So in the end, what you get is a uniform distribution of indirect light paths from all projector pixels to all camera pixels. Yes?
Does discretization of pixels play some important role in getting the complementary epipolar pattern?
So of course, this is assuming perfect optics, and that you can, and in practice, you're not dealing with perfect optics. You're dealing with discrete pixels, and that can introduce errors as a result. And I'm not going to go into much detail about the codes beyond the fact that these are complementary to one another, but there's ways to make these codes more robust to discretization error, for example. So rather than deal with perfect complementary patterns, you might want to make these patterns a little bit thicker to ensure that if there's any miscalibration or if there's discretization error in here, that you are able to compensate for that. So we built a setup that was able to do this. So we started with a projector that's used to illuminate the scene with a sequence of patterns. And this is done at 4,000 hertz. And then we have a series of optics that focuses the light on a mask. And a mask physically implements those mask patterns that we place over a camera. And this is a digital micromirror device that consists of basically an array of little mirrors that can be flipped on and off. And every time a mirror is turned on, it'll redirect some light to a specific camera pixel. And so this part of this prototype system is used to effectively implement a coded exposure. You optically select which pixels on your sensor are going to be exposed at any given time. And this can be used to expose your sensor to different mask patterns at a rate of 4,000 hertz. So we can change the illumination at 4,000 hertz, and we can change the masks that are placed over our sensor to block light at 4,000 hertz. And what the probing procedure to capture indirect light looks like is as follows. So we implement that procedure I just mentioned by first illuminating a scene with these epipolar lines. And what we're illuminating here is this candle, which is translucent. And so what that means is light scatters through the candle, bouncing around multiple times before reaching your camera. And the candle here is actually in the foreground. So it's popping out. But you'll notice that these stripes actually just cut right through the image, as if they're not bending due to the geometry of the scene. And this is a property of those epipolar lines. And what that means is that because we know exactly where we're illuminating the scene, we can pre-compute what are the mask patterns that will block the direct light. So in this case, we are basically blocking all the regions that are receiving light directly from the projector using a mask pattern that we place over a sensor. And by doing so, what we ensure is that the only light that we're picking up here is due to indirect transport. It's light that's bouncing around multiple times before reaching the sensor. And we can repeat this process multiple times over the course of a single exposure to get this image. And this is an all-optical process, which means that we can start doing this for videos. So here we have a conventional video stream of water being poured onto a hand. And here's the indirect-only version. So there's no processing here. We're capturing this as raw footage coming out of the video, out of the camera. And all the processing is done through this sequence of illumination and mask patterns that we're basically displaying for each frame of this video. So every frame is the result of integrating 96 different illumination and mask patterns. And what's interesting about this video is that you get to see all these different effects that you wouldn't have seen otherwise. So for example, the water, as it gets poured on, it actually traps light between the film, the surface of the water, and the palm of the hand. So it lights up your hand, basically. It's light that's basically indirect light that's being introduced into the scene by pouring water onto the hand. And the hand, again, appears red because it's picking up the color of skin. And if we have our indirect-only image and our conventional image, we can take the difference to capture a direct-only image. So this image looks a lot more gray because you're basically only picking up the light that's reflecting off the surface of the hand. You're not actually picking up the color of the hand. And the water, when you pour it all over the hand, it looks a lot more flat. Basically, you're not capturing all the indirect light that makes this scene interesting. It looks a lot more dull in some sense. Here's another scene. So this is a furry hat. And the furry hat consists of all these translucent fibers that scatter a lot of light. And if you're to take the difference between the conventional and indirect-only image, you get this interesting looking object. So this almost looks like metallic fibers because the individual fibers on the hat are actually very specular. And you don't see it as much in the conventional image, but it has this kind of shine that basically as you move the fibers around relative to the light source, it'll specularly reflect light in different ways. There's some green artifact here, and it's a result of computing the difference between the conventional image and the indirect-only image when one of them has some saturation in it. So it's a result of the computational process of taking the difference between the two. So because we can control the amount of indirect light and direct light in this way, we can start using this kind of probing technique as a way to capture 3D shape in a much more robust way. So here we have our scene again, where we have our, let's say, a projector that's illuminating the scene and a camera capturing the response, but we have a lot of indirect light in the way. And if you're to use this kind of setup in order to capture 3D shape, you might want to use structured lighting. So you send a bunch of different illumination patterns out into the scene. This is a conventional technique that's used all the time. You send out, for example, different sinusoids, and then you process the results to get 3D shape. The problem is in these highlighted regions, the direct light and indirect light interfere. So we're sending out these kind of vertical stripes, but the mirror is reflecting these stripes at a slightly different orientation, and the overlap between the two produces some interference patterns. So it's this hatching pattern. And so if you're to just take these images as input to a reconstruction algorithm, you get this kind of reconstruction. Here's our indirect invariant imaging approach. It's very similar to the direct-only approach. The only difference is that the indirect light isn't removed here. It's just invariant to the patterns that we're sending out into the scene. And what that means is that, first of all, these are all raw images. It's the same sequence of patterns that we used in the previous sequence, except that we're only effectively structuring the direct component. And this is done by basically making use of a different sequence of illumination and mask patterns to capture these types of images. And what you'll notice is in these highlighted regions, you don't get the same interference pattern as before. And so what that means is that you can take basically this transport probing technique and combine it with existing structured light algorithms that project, say, a sequence of sinusoidal patterns out onto the scene and use the same reconstruction algorithm to get much better reconstruction to 3D shape. And so this type of reconstruction is typically very challenging to do. But by making use of novel optics and computation, we can effectively overcome some of the difficulties with scanning scenes that contain these spectral indirect effects. Now, some of you might have noticed that you can even, well, reconstruct the shape within the mirror. And the mirror is only including indirect light. So it's light that reflects off the mirror, off the face, back to the mirror, and into the sensor. So these specific indirect light paths actually do satisfy epipolar constraints, which allow us to perform the reconstruction of the object within the mirror as well. And we looked at different versions of probing as well. So there are a number of different ways to produce indirect-only images, direct-only images, and you can optimize for the patterns, the right patterns to use in specific instances. And the codes that I've been showing so far involve making use of are really designed for these DMD projectors. So DMD projectors are projectors where they use a mask that you place in front of a light source to produce a pattern. And that pattern basically blocks a lot of light. So if you have, say, only half the projector pixels that are turned on, as in the indirect-only transport probing procedure that I just mentioned, then you're wasting half the light in the process. But there are other types of projectors that you can make use of that will make the transport probing procedure much more efficient. So for example, you can make use of a laser projector, which instead of blocking light, you're basically raster scanning the scene with a ray of light. And that significantly changes how we perform probing and changes the patterns that we use for probing. And so one of the projects that involved this form of energy efficient probing, where we're looking to try to maximize the energy or light energy that we have available for probing, involved computing or creating a new setup. So this particular setup was constructed by my colleague, my co-author, Supreet Achar, who's now, as Steve cites, at Google. And Supreet came up to Toronto, and we built some prototypes together, and he went back to CMU when he was a student at the time and built this thing together. And this thing consists of a laser projector. It's a projector that basically raster scans the scene with a laser line, a pair of rolling shutter CMOS cameras, and I'll explain why these rolling shutter cameras are important for transport probing in just a sec. And we have some synchronization electronics. And what this setup does is basically very similar to what we were doing before. In this case, I'm showing you a transport probing technique for capturing the direct light within the scene. And it worked by basically using the laser projector to illuminate the scene one epipolar line at a time. So it's scanning left and right, up and down. And we use a rolling shutter camera to expose a select set of pixels on the sensor. So rolling shutter cameras work by basically rolling the exposure across your sensor. So it's selectively in sequence illuminating or exposing a specific row of pixels. And we can exploit that in this case and combine it with a laser projector and in order to perform direct-only probing. And in this case, we made sure that our projector and camera were rectified. So they're basically side by side. The optical axes for both systems are basically in parallel to each other. And that ensured in this case that the epipolar lines are horizontal to one another. And so they align with the rows of your sensor, and they align with the way the laser projector is scanning the scene. And this has an added benefit as well. So the added benefit here is that in addition to probing only the direct light path in the scene, which means that you're getting much more robust information for 3D shape, you're also effectively significantly reducing the exposure time of your sensor. So here, we're getting all the direct light from the projector. So we're not wasting any light whatsoever. So all the light from the laser projector will transmit to the scene, and it will always reach the camera and get picked up. Now, by making sure that the camera pixels are only on for that specific instant in time and not throughout the entire exposure period, we ensure that those camera pixels receive very little contribution from any other light source, say an ambient source within a room. And so that's great, because what that means is that, sorry about that. All right. So through that transport probing procedure, we can produce images like this one. So in both cases, we're projecting these structured light patterns into the scene for capturing 3D shape. But on the left is your regular image that you would capture with a sensor. And on the right is the case where we only selectively turned on specific camera pixels when they're being illuminated by the laser. And so you get the same amount of light from the pattern that you send out into the scene, but you're effectively reducing the amount of ambient light that's being picked up by the sensor. And so what that means is that you can see the patterns on the light bulb, even when the light bulb's turned on. And this is particularly useful for doing imaging, 3D imaging, outdoors under very bright sunlight. So in both cases, we have structural light patterns being sent out in the scene. Turning down the aperture here doesn't help at all, because the ambient light is so strong, it basically drowns out any signal that's being captured by the camera, from the projector, I mean. But on the right, we can basically reduce the amount of ambient light that's being picked up, and that allows us to see the structural light patterns, which allow us to basically capture 3D shape, even under these harsh scenarios. So another student from CMU, Joe Bartels, took one of our sensors, our camera systems, and brought it out to the NASA Research Ames facility out in California. And there they have basically an environment that simulates Mars, and they have these little rovers that drive around. And so put one of these cameras onto one of these rovers. And in this case, we're making use of active stereo to perform imaging. And the idea behind active stereo is that our prototype system actually had 2 cameras on there. In this case, we're using both the information or the images from both cameras to basically interpret 3D shape. So we're basically doing stereo. The active part comes from sending out texture basically into the scene with the projector. And so on the right here, the challenge is that with stereo or active stereo, the dynamic range of the scene is so large, the brights are so bright and the darks are so dark that the information cannot be captured by the camera in one shot. And so that makes it really hard to simultaneously capture the shape of objects that are well exposed and regions that are underexposed. So either you extend the exposure period or open the aperture to expose regions that are in shadows to get shape in those regions, or you close the aperture and shorten the exposure period to get better 3D shape in regions that are bright. But on the left, because we're reducing the amount of ambient light that's being picked up, and we're basically amplifying the amount of projector light that we're interested in, we can get more complete coverage of 3D shape. So a lot of that focused on capturing the 3D shape from direct light paths. But there are situations in which you don't have any direct light paths to work with. And that occurs when, if you want to image an object here of a bunny, you want to capture its 3D shape, but there's an occluder in the way, the only way we can actually illuminate that bunny is through indirect light transport. That is, we can send out light patterns out onto a wall, and some of that light will scatter and hit the object, and eventually some of that light will scatter back to the wall, and then you pick it up with a sensor. Now, in order to do this, this form of imaging makes use of, so we started basically working with these SPADS sensors. These are sensors that stand for single photon avalanche diodes. These are time-of-flight sensors, and they're very sensitive sensors. And the way they work is that you start with a laser that sends out these packets of light into an environment, and you measure the time it takes for light to travel through the environment and hit the sensor. And in this case, what happens is that when an individual photon hits the sensor, it basically creates an event. The SPAD sensor is sensitive enough that it can pick up individual photon events, and every time a photon gets picked up, the sensor basically outputs a timestamp for that photon. And that timestamp corresponds to the time it takes for light to travel from your laser through the scene and onto the sensor. Now, this process is repeated multiple times, typically. In our case, I'm going to show you experiments where we repeat this process 10 million times a second. And after, say, 1 second, you get 10 million events that represent photons that came and hit the sensor at different instances in time. And so what you output from the sensor is a histogram of the distribution of arrival times for these photons striking the sensor. And this is particularly useful for imaging objects that are hidden in this way, because we can use a SPADS sensor to pick up a histogram that consists of light paths that hit the object or hit the wall here and come straight back, and light paths that basically hit the wall, hit the hidden object, come back to the wall before being picked up by the sensor. So this histogram is an example of a measurement that was captured with one of our systems that we had built. And there are 2 peaks here. So on the left at time 0, I've just placed that at time 0 for simplicity, it represents the light that comes straight off the wall. So it's light that you send out into your environment and the light that comes straight back to the sensor. But a little later in time, there are a few photons that come back at, say, 4 nanoseconds in time later, so after hitting the wall. And that consists of these indirect light paths that travel, hit the wall, hit the object, hit the wall, and come back to the sensor. And if you want to, say, image how far this object is from the wall, all you need to do is compute the difference between the arrival times of these 2 peaks. And by the way, this scale here is logarithmic. So these little peaks are very, very small relative to the direct light. There's very little light that actually scatters 3 times before being picked up by the sensor, which is part of the reason why we're relying on these SPADs for imaging, because they're extremely sensitive. So this is an example of what a SPAD outputs. So this is being output at around 10 frames per second. And on the right here is a video of David. This is a student at Stanford that I've been working with closely on this project. And he's holding up this exit sign. And at time 0, you get the light from that's coming off a wall. So we're illuminating a wall and imaging the response at the same point on the wall. And this little spike here represents the light from a exit sign that's scattering light or receiving light from the wall and then scattering light back to the wall. And the distance between that small peak and time 0, where we have the direct light here, corresponds to how far David is from that particular point on the wall. So this is great. So what you can use this for is to identify whether there are objects that you might not be able to see directly by picking out whether there's a peak present or not. And then you can figure out its distance from the wall by measuring the difference in time between that small peak and this large peak. By the way, the exit sign here is retroreflective. And that's significant in this case because it helps us actually improve the signal. Retroreflective objects basically reflect light back to its source. So as opposed to a diffuse object, these retroreflective objects are helpful in that they significantly boost the indirect light here, which allows us to do imaging under ambient lighting. So these indirect light paths allow us to capture how far an object is away from a wall, but you can go a step further. And so this was explored by Andreas Velten and Ramesh Raskar at the Media Lab a number of years ago. And the idea was that instead of just capturing one measurement, you can capture a whole range of different measurements in order to actually reconstruct the shape of an object hidden around a corner. And by looking at different path lengths, you can solve a complex optimization problem to recover this 3D shape from the measurements. And it worked as follows. So on the right here, I have a hidden volume, and I'm illuminating a wall at the top with a laser. Some of that light scatters, and then some of that light will fall on a hidden object. And this object will scatter light back to the wall, and it'll get picked up by a sensor that's looking at a different point on the wall. So as opposed to, say, just looking at one point on the wall, you capture the measurements along a whole different array or grid of points on the wall, and you get measurements that look a little bit like this. So this is a spatial temporal streak, and its shape is given by how long it took for light to travel from one point on the wall to the object and another point on the wall. So for example, this particular point on the streak corresponds to the length of this light path, and the apex of the streak corresponds to the point on the wall which is closest to the scatterer. Okay? And the shape of the streak is actually related to something that we call the Minkowski's light cone. Minkowski's light cone describes how light propagates from a singularity in space and describes how it propagates both in space and time. But I'm not going to go into that into too much detail here. The important part is that there's a streak that corresponds to a scatterer within the hidden volume. And if you have a bunch of different scatterers, you get a bunch of different streaks. And it's a linear superposition, which means that there's basically a linear system that describes a relationship between an unknown volume and the measurements that are captured with a system like this. So that's great, because what that means is that if you capture, say, measurements, temporal measurements for how light reflects off a hidden object and back to a wall, you can just create a matrix A. A is known based off of the geometry of the wall and how light transport interacts with hidden objects. And all we need to do is invert A in order to recover an image of the hidden scene. The problem and most difficult aspect of this problem happens to be the size of the matrix A. So in practice, what we're dealing with is matrices that are about n to the power 6 elements in size. And that's because we're trying to map 3D volumes to 3D volumes. We're trying to map a 3D measurement volume to the 3D geometry of the scene. And so if you want to invert that, you're going to run into some problems because it's so large. And so there have been two solutions done so far. The first, which is the original method, is to just approximate the solution of from the measurement. So instead of inverting the whole system, you can just compute the transpose of the matrix A, which is much more efficient to compute. And you get the result, and you can apply some heuristic filters to try to sharpen the results, and you get some images that look a little bit like this. Another solution is to try to simply do your best. Essentially, you either reduce the resolution of the volume or measurements that you're working with, and then you invert the system. And the challenge in both cases is that it requires a huge amount of computation. For example, this can take on the order of tens of minutes. On the right, it can take on the order of hours to compute a solution. So we wanted to take a slightly different approach. So instead of trying to solve this complex inverse system, our thought was, what if we can manipulate light transport? What if we can select the indirect light paths in such a way that it simplifies the reconstruction problem that we have to deal with? So instead of just arbitrarily sampling the wall with our laser and sensor, we can try to do two things to make this problem easier. The first thing is to try to what I call confocalize our measurements. So instead of illuminating one point and then imaging all other points on the wall, we can illuminate and image the same point on the wall and then scan both the laser and detector together across the wall. And what you get in this case is a slightly different set of streaks. And what's interesting about this set of streaks is that the scatterers that are all at the same distance away from the wall actually produce the exact same shape for the streak. And that's a nice property to have, because then for those particular scatterers in space, they're basically related to the measurement through some deconvolution process. So it would be very easy to solve for a particular plane and depth by making use of these confocal measurements. The problem now is that you have different scatters at different positions and depth, and those produce different streaks of different shape. So we can introduce another step, and that is to perform a change of variables on the measurements and unknown volume. And this change of variables basically stretches the two in order to make the streaks also basically produce the same shape for different scatters at different positions and depth. So by basically confocalizing the measurements and stretching the measurements, what we've done is we've basically created a relationship between our measurement volume and the unknown volume through some blur kernel. And this is fantastic because all we need to do now to recover an unknown volume from these measurements tau is to basically do a deconvolution. We compute the Fourier transform of this, do a division of the Fourier coefficients, and an inverse Fourier transform to get a result. And so we can produce images like this on the right in a much more efficient fashion than before. So as opposed to, say, 10 minutes for a back projection method, this type of approach only takes 1 second. And even better is that we're not approximating a solution. We're getting the exact solution that we're trying to go after. So by manipulating light transport and probing for specific light paths, we can actually greatly simplify the reconstruction process in order to perform 3D acquisition of indirect objects. So here's the whole algorithm. So we start with some measurements. We do some stretching, and then just perform a simple deconvolution to recover the hidden result. So there's an unstretching operation after the deconvolution in order to recover the final 3D shape. And we can do this in 3D as well. So instead of just scanning, say, a 1D line on a wall, we scan a 2D set of points on a wall, and it's the exact same process. So we start with a measurement volume, we stretch it out in time, and we do a simple deconvolution to get the result. And so we did this in practice. So we have our system on the right, our hidden object on the left, and a laser illuminating the wall. The object in this case is 125 centimeters away from the wall. And our laser is very, very faint here. It's faint because there's so much ambient light. But despite that, because in this case our object was retroreflective, it helped us with capturing the indirect light. And by the way, the only way to exploit these retroreflective objects is through confocal scanning. So confocal scanning not only helps us reconstruct objects faster, it also allows us to capture hidden objects, even in cases where there's a lot of ambient light to deal with. So we are scanning the scene, and the laser dot here is actually moving, but it's extremely faint. And what we capture is a measurement volume like this. And what I'm going to show you is different temporal slices of this volume. And you'll see these different streaks passing through the volume. So this is raw data. It comes out of a system like this. And in less than a second, you can recover a hidden S. And so we did this for a number of different objects. So in this case, for example, we have a mannequin. And this is done in an indoor setting. So we have a little bit more control over the quality of the measurements that we're capturing. We also took longer exposure periods in this case. And we're able to reconstruct images, 3D images like this one. Here's the exit sign, which I showed an image of before. This exit sign is about 2 feet wide, 2 feet tall. And we compared our reconstruction method to back projection as an example. In back projection, again, it takes around 10 minutes to compute, and you get nowhere near the quality that we do in less than a second. Here's another example, an S and U. Yep.
On the sign, how are you picking up color or depth? The photon's being absorbed?
Yeah, so the sign, the reason why white looks white and black looks black is because the white is what's scattering light. So it scatters light back to the wall, but the black regions of the sign won't scatter any light. And so that's why you can recover the letters on the sign. So here's another example. In this case, we have an S and U that are occluding one another. So one's in front of the other and blocking certain light paths. And this shows that it's actually, our reconstruction algorithm is relatively robust to even situations like this. And this works for diffuse objects as well. So the only difference between a diffuse object and a retroreflective object is the amount of light that's available. So if you just take longer exposure periods, you can do a lot better. And I should also mention that we incorporated our procedure, which is LCT, light cone transform, based off this hypercone that I was mentioning before, Minkowski's light cone. And we incorporated these priors in order to introduce smoothness constraints, or basically smoothness priors to get better quality results. We also take into consideration the characteristics, the noise characteristics of our sensor, as well as non-negativity constraints on the volume that we're trying to reconstruct. And I'm trying to do this now in real time. So this is done right before I got here, actually. So there's an object here on the top, which consists of 2 vertical stripes. And we're a camera in the bottom and an occluder in between. And on the right here is an image from the perspective of the wall. On the top is a top-down view of the object. And what you see is these 2 vertical stripes. But what's interesting here is that this is being done every 2 seconds. We're doing this at half a hertz, and I'm moving this object around rotating it around, and we're able to reconstruct this thing very quickly. The thing that's holding us back right now is the amount of light that we have available. And we're currently using actually a very low power light source, so we can simply improve the quality of that light source, increase the power in order to even reduce this even further, the acquisition time, that is. And what's particularly exciting about this is that what we've actually implemented is effectively a LiDAR system. It's the system that basically you can focalize the detector and laser and then scan the scene. And like LiDAR, we're measuring time of flight. The only real difference is that in LiDAR, they're only interested in the first reflection, whereas we're really looking out for the indirect reflection, the light that comes after the first bounce. And so there's a lot of hope for, or I have a lot of hope for actually trying to make use of existing LiDAR systems to implement some of our reconstruction algorithms to start seeing objects that might be hidden, say, around an intersection. I just want to quickly point out a couple of works that I've been working on related to these SPADS sensors. One is transient imaging, is that these SPADS sensors allow you to measure the time of flight of objects interacting with the scene at very, very short timescales. And so we can capture videos of light propagating, say, through fibers. And this is a new form of imaging that allows us to analyze scenes and see scenes in a completely new way. It also allows for extremely low, very energy efficient probing of scenes. For example, if you want to image the 3D shape of scenes in a case where you have a lot of ambient light to deal with and maybe a very low power light source, you can make use of SPADS plus convolutional neural networks to actually very efficiently recover the 3D shape from noisy volumes. And I'm particularly interested by techniques like OCT, optical coherence tomography, which is a form of time of flight sensor as well. And we're looking to see if we can apply some of these non-line of sight imaging techniques to OCT. So overall, I want to just reiterate that light transport probing allows us to perform all these different imaging tasks for capturing the 3D shape more robustly, dealing with indirect light, dealing with ambient light, and even dealing with cases where you don't have direct line of sight with an object. And more generally, computational light transport, while I focused on the acquisition of 3D shape, there's a lot of different applications for this kind of area. That is, there's a lot of different techniques that make use of both active lighting and sensing in order to perform a wide variety of tasks. For example, OCT is an imaging technique for imaging the retina. It's used by ophthalmologists. It's a form of active lighting. These types of techniques are also used in film to basically take an actor, measure an actor's performance, and then digitally put them into a virtual environment with all the right lighting conditions. And more generally, computational imaging is this idea of kind of changing the hardware and software of cameras and displays in order to really augment what we can do with these kinds of systems. And I think that these are the first steps to try to really make an impact in different areas and provide a new way to think about some of these problems that involve imaging. Thank you.
Questions?
Yeah.
A very naive physical question. It seemed like very little of what you did required using wavelengths in the visible spectrum. So why not, go invisible?
So visible spectrum makes it just easier to work with. So the projectors I'm using are commercial projectors that are being sold off the shelf, and they just have red, green, and blue or LEDs in them. So it was easier to work with. It's also easier to see, so I can calibrate things. But there's nothing stopping you from moving to a different part of the spectrum, of course. In fact, it'd be nice to move to a part of the spectrum where ambient light doesn't affect you as much. And so that you can use some of these techniques in parallel with different properties at, say, the infrared domain, where you can start pushing basically energy efficiency a lot more because you have a lot less ambient light to deal with. Yeah?
So with regard to your imaging the occluded objects, first, you're observing the light coming from a wall, or reflected from a wall. If it's not a wall, but something very complicated, like what you would see in real scene, how does that affect your system? And you at the beginning you show like a histogram, and you're like probing the second peak or third peak, and I saw your result like U and S, one including another, and you can pick up not just the second peak and multiple peaks. And so, like, is there a limit how many stuff you can?
Right. So there are two questions there. One was, how can you deal with more general surfaces for indirect imaging or non-line of sight imaging? So the outdoor example that I showed you actually had a lot of texture. So we're imaging off a brick wall that had a bunch of variations in albedo. And that's an example where different parts of the wall will reflect light in different ways. So it was robust to that. One of the assumptions I didn't point out was that we're assuming that the surface that we're imaging off of was flat, so that all these structures that we're trying to exploit assume a flat surface, and we're looking to generalize that to surfaces that might be curved. Regarding the second part of your question, we are not explicitly picking out a single peak, but we're actually using the full temporal impulse response of the indirect light. So we're looking for the direct peak, and then we eliminate that, we ignore it, and we just look at everything else that comes after. It's not always a peak. Sometimes if you have a more complicated object, it might be several peaks. But it's precisely that information that we're capturing and then using for the inverse process. Yeah?
So do you expect that you'll be able to get single photon avalanche detector cameras, like complete 2D arrays of these things, and then what would that get you?
Right. So there's a lot of work going into the space right now. So we, at the very end, I showed you a couple quick slides. Some of those measurements or results were created with 1D SPAD detectors. So we have 256 pixels as well that we can use to scan a room. And if you have a 2D SPAD array, which is also being developed, there's some research groups out in Switzerland where we got some of these sensors originally that are creating these 32 by 32 SPAD arrays and allow you to capture all this in a single shot. So it might be possible to simultaneously capture all this information in a single shot by not just floodlighting the room, but maybe making use of the original, what I was talking about in the beginning, where you use coding and masking to select specific light paths and combine it with non-line of sight imaging.
All right, so let's thank the speaker again.